Welcome to this lecture series in chemical reaction engineering. We'll continue with problem solving from chapter number 7. So 7.12, reactant A in liquid either isomerizes or dimerizes as follows: A giving you R, which is desired product, and A plus A, that means 2A giving you S, which is undesired or unwanted product. The rate laws are given. Rate of formation of R is K1Ca, rate of formation of S is K2Ca square. So reactions are first order and second order. We have to solve this problem in 4 parts: A, B, C, D. First, we have to write R by A and R by R plus S. So instantaneous yields we will write. Then with a feed stream of concentration Ca0, we have to find Cr max, which can be formed by these reactions in plug flow reactor and in mixed flow reactor. This is part B and C. And the last part is on batch reactor. A quantity of A, initial concentration Ca0 is equal to 1 mole per liter, is dumped into a batch reactor and is reacted to completion. So reaction is complete, means 100% conversion. Ca final will be 0. If Cs, this concentration, is 0.18 moles per liter in the resultant mixture, what does this tell of the kinetics of the reaction? So rate law is given, orders are known, but the rate constants are not given. So we don't have complete information on kinetics. So we'll solve this one by one. So part A. Now here we have to note that first reaction is A giving you R and second is 2A giving you S. So minus RA, rate of disappearance. So A is disappearing in the first reaction and in second reaction. Here 1 mole is involved, here 2 moles are involved. So RS and RR is given. So we have to bother about this stoichiometric coefficient. So minus RA by 2 will be equal to plus RS. That means minus RA is equal to 2 times RS. So RR is K1Ca. RA is first reaction K1Ca, and for second reaction we have to add this 2 here. So multiplied by 2 K2Ca square. So R by A is defined like this. Instantaneous yield in terms of R by R plus S. Now it would have been same terms if stoichiometry would have been 1:1. It is not. So this is different now. So RR is K1Ca, whereas RS is K2Ca square. Okay. Instantaneous yield R by A is dCr by minus dCa, which is this equation, and K1Ca will divide numerator and denominator throughout by K1Ca. So this becomes 1. This term becomes 1. 1 plus K2 K2 by K1 Ca. This will remain in the numerator. So for Cr max, C is equal to Cr max. That means this R should be 1. Maximum possible is 1, which will be there when this Ca final is 0. Complete conversion is there. So we'll see now for plug flow reactor. We have this Cr max. This we know this term 1 upon 1 plus 2 K2 Ca by K1. Model tells us that Cr max is integral Ca0 to Ca final with minus sign. So if I make this sign plus, I will reverse the order. Now here Ca0 to Ca final is 0. So I am writing now 0 to Ca0. To solve this, I will set the numerator to be log of denominator. If the not log of denominator, if numerator is the derivative of denominator, then our integration is log of denominator. So we have to set this. What will be the derivative of this? 2k2 by k1. So I want 2k2 by k1 in the numerator. So what I have to do? I have to take out this K1 by 2K2, okay, common, which is outside. So what I have done, multiplied and divide by this value. So this numerator is same as the derivative of denominator. So K1 by 2K2, this is constant, we have taken outside, okay. So K1 into ln of 1 plus 2K2 by K1 Ca from 0 to Ca0. If you substitute lower limit 0, this becomes 0, ln of 1 is 0. So only first term is left, that is 1 plus 2K2 by K1 into Ca0. Ca is replaced by Ca0. So this gives you equation for Cr max in plug flow reactor. Okay, that is what we can say, because if Ca0 is also not given in that part, K2 and K1 values also we don't know. So we can write an expression in terms of K1, K2 and Ca0 for plug flow reactor. For mixed flow reactor, Cr max is this instantaneous yield at exit multiplied by Ca0 minus Ca at exit, at Ca final. Ca final is 0. So this is simply Ca0 into phi of f, and phi of f is 1. It is going to complete conversion. So Cr max will be equal to Ca0. So whatever value of Ca0 you begin, there will be complete formation of Cr at that. Okay. Now third part is in batch reactor. It is given Cs is given as 0.18. We know Cr is equal to Ca0 minus Ca minus Cs. Ca0 is 1, Ca finally is 0, and this is minus 0.18. So Cr we get at this value of Cs, it will be 0.82, and it is mentioned that in batch reactor it goes to complete conversion. Okay, that is mentioned in part D. So what we have to find out is, we have to find out this value for Cr is equal to 0.82, which value of this ratio K1 by K2 or K2 by K1, whatever, this ratio we should use so that we get this value as 0.82. Okay, so we will use that for batch reactor. So you can go for trial and error, K1 by K2, 1, 2, 3 and so on. In between we have found that this value 0.82 is reached at K1 by K2 is equal to 4.27. Similarly, if you plot this is the equation, this one, substituting different values of K1 by K2 and finding out Cr. So this is from that equation of plug flow reactor. And why we are using plug flow reactor equation in batch reactor? Because you know plug flow reactor model and batch reactor models are same. Only difference is there we define batch time t and here we have space time tau. So same equation we can use, or same model we can use for batch reactor. And Cr is equal to 0.82 constant. This is another equation. So Cr is equal to 0.82. You draw this line. So Cr is constant, means it will be parallel to x-axis, and where it intersects this point, and this point is 4.27. So graphically or by trial and error you can find out, and this value comes out to be 4.27. So in batch reactor, when you start with 1 mole per liter and obtain Cs is equal to 0.18, we find that Cr obtained there is 0.82, and if I want this 0.82, I have to maintain K1 by K2 as 4.27. Okay, and here you can see K1 is 4.27 times K2. That means very high. So we are getting maximum R. Okay. So in part B and C in plug flow and mixed flow reactor, this Ca0 is not given, whereas here it is given, numerical value is given. So here our analysis is just qualitative. Okay, and what we can say is only this Cr will be Cr max at Caf is equal to 0 when complete conversion is there, and Cr max will be given by this equation where K1, K2, Ca0, these are unknown, but if you know these values, this works. And plug flow reactor, we know the relationships, so we can find out in case of batch reactor, and that we have seen. So what you can say about the kinetics means, we can say that this ratio is to be maintained 4.27 so as to obtain this maximum conversion 0.82. Okay, because CS formed is known, so this is fixed and this is maximum possible in this case. Next, 7.30. In a reactive environment, chemical A decomposes as follows. A gives R and A gives S. Rate of formation of R is Ca. Rate of formation of S is 1. So this is first order, rate constant is 1. Here also rate constant is 1, it is 0 order. For a field stream of Ca0 is equal to 4 moles per liter, what size ratio of two mixed flow reactors will maximize the production rate of R? Also give the composition of A and R leaving these two reactors. So you have to find out concentration here and concentration here for ARS. So we write instantaneous yield dCr by minus dCa. So this is Ca by 1 plus Ca. So here the extreme conditions are Ca is equal to 0 or Ca tending to 0, very low value. This will be 0, and Ca tending to infinity, it will reach to 1. So from 0 to tending to infinity, let us say 0 to 1000, some value. It will be varying from 0 to 1. Now for first reactor, we will apply mixed flow reactor model. CR1 is equal to this R by 1, we are using subscript 1 for first reactor or reactor 1. So instantaneous yield from the first reactor into minus delta Ca. So this is known. This is Ca by 1 plus Ca. So reactor 1 subscript 1 we add Ca1 by 1 plus Ca1. And delta Ca will be Ca0 minus Ca1. Okay. This is minus delta Ca. Delta Ca is Ca1 minus Ca0. So Ca0 minus Ca1 into Ca1 divided by 1 plus Ca1. So what we know is Ca0 is known, that is 4. We want to maximize this CR1. So dCr1 by dCa1, with respect to dCa1 you differentiate and equate to 0. So apply quotient rule. So denominator into derivative of numerator. What is numerator? 4Ca1 minus Ca square. 4Ca1 minus Ca1 square. So 4Ca1 minus Ca1 square, derivative of the denominator 1 plus Ca1. So this is as it is 1 plus Ca1, derivative of this ddCa of 4Ca1 is 4. ddCa, here you can write this or write ddCa by derivative with respect to Ca1. Anyway, so this is done. So this is as it is, and derivative of this term with respect to Ca1. So first term derivative is 0, second term derivative is 1. So this multiplied by 1. We are equating it to 0. So don't bother about the denominator term, which is denominator square of this term by quotient rule. So equate this to 0. So if you solve these brackets, you get a quadratic equation minus CA1 square minus 2CA1 plus 4 is equal to 0, and solution of the quadratic equation significant root is 1.236. You will get two roots, one will be significant, that you have to decide, and 1.236 moles per liter is Ca1, that is concentration of A leaving the first reactor. So from first reactor, this value, at this value you will get CR as CR max. So substitute this value of Ca1 in this equation. So Ca1, Ca1, Ca1. So we have substituted this Ca1 1.236 here, here and here. So you get CR1 as 1.52, and this is the maximum possible value of CR in reactor 1. CS1 at, you can say at CA1 value or the CR1 max value, it will be simply initial value is 4 minus CA1 minus CR. So total of CA1, CR1 and CS1 will always be 4, that is CA0. So 4 minus this also comes out to be 1.236. Total will be 4. For reactor 2 now, CR2. So instantaneous yield for reactor 2, we write this phi of R by A 2, subscript 2 we are using. So CA2 here minus delta CA is CA1 minus CA2, because delta CA is CA2 minus CA1 divided by 1 plus CA2. We know CA1 here, which is the stream concentration coming out of the first reactor. CA1 is 1.236. CA2 we have to maximize, so dCr2 by dCA2, derivative of this. Again same method, quotient rule. This you can write as ddCA1 and here also ddCA1. So we have done this many times. I will not explain this now. It's not necessary. And anyway, this is 12th class mathematics. Finding out maxima. Minus Ca2 square minus 2Ca2 plus 1.236 is equal to 0. And this you solve, your significant root is 0.495 moles per liter. This is value of Ca2. Similarly, you find out this Cr2, which is the maximum value, you can say, at this. So substitute this value of Ca2 here in this equation. Okay. So Cr is maximum at this value of Ca1. So this value we get is Cr2 maximum. And this is 0.245. Okay. Coming out of the second reactor. CS2 will be, what is entering the reactor? This 1.236, and Ca2 and Cr2 you subtract and finally you get 0.496. Okay. So here you can see, though this is the maximum possible value, but this value is less than both these values. That is finally coming out of the second reactor. That means finally coming out of the system. Cr max is 0.245 only. Whereas here this value is more than both Ca1 and Cs1. So this we have found out. Total of this must be 1.236, because we have found out it from that concentration 1.236. Okay. Now this we have found out by directly using the models and using the concept of maxima. So two times we have differentiated in reactor 1, reactor 2, found out the Ca2 value, then Ca1 value. Ca1 was intermediate value. This we have done. So we have two reactors in series. So this we can do by graphical method also. So here all the calculations have been shown. uh, 4 to 1.236, this is our, we'll say 1 instead of 1 2, we will write this is our first reactor, and from 1.236 this is our second reactor. So this reactor is placed first. We start with Ca0 is equal to 4, we get Ca1 is equal to 1.236, that goes in the second reactor, and from 1.236 up to 0 we have done this calculation, but anyway it is not going to completion. So here we are finding out these values. So in first reactor this was found to be 1.236 Ca1. In second reactor it is Ca2, that value is 0.495. Corresponding these values of Cr1 0.245, 0.496, 1.528, 1.236. So by calculations also, if you prepare a Excel sheet, so for first reactor and for second reactor we can find out. So what we have done earlier, it is we have just differentiated and found out in both the cases what should be the value of Ca1 and in second reactor Ca2, which will give you maximum R by differentiating this, doing our differential calculus. Here we are taking the data, and if this is from 1 to 1.23, this is from 1.236 to 0. Now these points are to be located, and that can be done by graphical method. So forget about the first part, we have done directly by taking the derivative equating to 0. You can do it by graphical method also. So this is our curve. Instantaneous yield R by A as a function of Ca. Here we are starting from 4. So on this curve, in the first reactor we want to find out this intermediate, okay, and this comes out to be 1.236, which we have found out in first reactor Ca1 1.236. So this method is not very easy, you have to do trial and error, but I will explain it to you. You can do by the method we have used already, just differentiate whatever you find easy. Now here you can see we have to adjust this point on this curve such that from this, if you draw this rectangle, the slope of the diagonal of the rectangle should be equal to slope at this point from where you have completed this rectangle. These two slopes should match. Slope of the tangent at this point and slope of this diagonal should match. Then you find out this intermediate point. That is the best possible point. And that is 1.236 found out graphically. Then second reactor from here to this value. Okay. And up to which value it is going? 0.495. So though our curve is from this 4 to 0, we have taken the points. Now here you have to find out again a point, second point on the remaining curve beyond this point 1.23. So this is our curve. So you have to locate this point such that from this point, if you draw a straight line and draw this diagonal, slope of the diagonal and slope of the tangent at that point should be same. So that is your best point in the second reactor, and this is here coming out to be 0.495. So you can see this is 0.2, 0.4, 0.6, 0.8. So here somewhere we have 0.5 and just somewhat less than that. So these 2 points are located here. for CR max. Now here you can see concentration of CR for the first reactor. You are starting from 4 and reaching somewhere in between. So here this value is maximum in this range, and here this value is maximum. Rest of the things you can see. So by locating the best point that you can do for this, uh, here some practice and some trial and error required, but still you can get very good results or accurate results, and that you can always match by taking that derivative. So whichever method you find suitable for yourself, you can do it. Solve the problems by that method in your examination if it is asked, but mostly the question it will not be mentioned solve by this method or that method. Next problem, consider the parallel decomposition of A of different orders. Determine the maximum concentration of desired product obtainable in plug flow and mix flow. So this data, A gives R, A gives S, A gives T, three competing parallel reactions. Minus R is equal to 1, 0 order, minus rate of formation of R is 1, that is 0 order with rate constant 1. Rate of formation of S is 2Ca, rate constant is 2, order is 1. Rate of formation of T is Ca square, rate constant is 1. So this is to be used for a set of problem, next three problems. So in plug flow and mix flow, maximum concentration of desired product obtainable. Now in first problem, it is mentioned that R is desired product and Ca0 is equal to 2. R is desired, so I will write instantaneous yield for R by A, that is dCr by minus dCa. Okay, dCr rate of formation, this is 1, minus dCa, you have to add all three, 1 plus 2Ca plus Ca square, and that is nothing but 1 plus Ca whole square. Ca tending to 0, Ca tending to infinity, you can test these conditions. When Ca tending to 0, instantaneous yield will be 1. When it is tending to infinity, instantaneous yield is 0. Plug flow reactor and mixed flow reactor. So first plug flow reactor, this you know, Cr max is equal to, this we have already used. Here with this minus sign we have reversed the order. So from 0 to 2, 2 is Ca0 value which is given. 1 upon 1 plus Ca whole square dCa. So everything is given. You solve this integral. Simple. 0.667. We have done it this many times. Okay. 0.667. Also you can plot this Cr versus Ca. Okay. As this functions, and this value is here 0.667 maximum. So you start from 0 and all these points. So Cr max is 0.667. Only calculating this is sufficient. Mixed flow reactor, it is again Cr max, we have done this earlier. This is Ca final is 0. So this into Ca0 and Ca final is 0. So this is 1. So Cr max will be 2. You will get complete conversion to Cr for this case in mixed flow reactor. Next problem 7.15. Now here S is desired product and Ca0 is 4. So S is desired product, so DCS is 2Ca and denominator remains same, 1 plus 2Ca plus Ca square, which can be written as 1 plus Ca whole square. So for very low value of Ca tending to 0, this yield will be 0, and for very high value of Ca tending to infinity, this also will be 0. So this you can check from the data. Now in plug flow reactors, CS max will write. Earlier we have seen CR max. Now this is for CS max. So only difference is you have to replace this yield in terms of S. So phi of S by A. This is 2CA by 1 plus CA whole squared. This 2 constant we can take outside the integral sign. Here I have written it outside. And remaining integral is CA by 1 plus CA square. Okay, so it is nothing but integral x dx by a plus bx whole square. If this kind of form is there, then the analytical solution is 1 by b square into bracket ln of a plus bx plus a by a plus bx. Now for these different forms, if you really remember these forms, then you can go for analytical method. And most of the times it will be difficult to remember all possible forms. So best way is to go by numerical methods or go for graphical method. Graphical method is simplest. Integral y dx, this is y. What is on y axis? Y. This you can calculate for various values of CA. Find out this from 0 to 4. You can take 10, 15 values, whatever, and calculate immediately and plot this area under the curve. Measure the rectangles properly, and that will give you the value of integral solution. Or go by numerical methods. I have explained you one. You can take step size of 0.4, minimum 10 points you should take. So n plus 1 is equal to 10 means n is equal to 9, and that divided by 3 should be integer, so it is 3. So I have explained you one method, numerical method, simple, that you can use always. Always take 10 points, and it's very simple to follow. So go for numerical method, solve by graphical method, or solve by analytical method. It's your choice. So CS max, this 2 is coming from here, which is outside, and CA by 1 plus CA square. Okay. Now CA is X. A and B, what are the constants? A is also 1, B is also 1. So this B square, this becomes 1. Only 2 will be there. ln of 1 plus CA. This is 1. Then 1 upon 1 plus again CA. 0 to 4. So you solve this and you get CS max as 1.619. Okay, this is given as 4. Units may be anything. Units are not mentioned, so we are not mentioning the units here. Now this solution is sufficient if you are able to do it. Then you can calculate the CA and instantaneous yield in terms of phi of S by A. So this small phi is by A, and from 4 to 0. So this is marked 4 to 0. So you have to count these rectangles and find out. It will give you CS max, and that is 1.62. So it's almost matching perfectly. If you count the number of rectangles properly, this value must match. But plus minus 2-3% error, as I always told you, it is acceptable. Then mixed flow reactor, second part. CS is equal to this equation now you know, and this is 2CA by 1 plus CA whole square, 4 minus CA. So this function. So if you maximize this for dCs by dCA is equal to 0. So again quotient rule, I will not explain this. Denominator, this is denominator is 1 plus CA whole square, or denominator becomes 1 plus CA raised to 4. But anyway, this is equated to 0, so that otherwise This is C1 plus CA raised to 4. If it is not 0, then it's very difficult. You have to expand this and see, collect the terms and so on. So problem is easy for us. You have to bother only about the numerator term. And from this, if you solve, you get a quadratic equation. Minus 12CA square minus 4CA plus 8 is equal to 0. And from this solution of quadratic equation, this significant root is 0.667. CS max at CA is equal to 0.667. So in this equation, you substitute this value 0.667 everywhere. So here 0.667, 1 plus 0.667, this is whole square, 4 minus 0.667. So this you get as 1.6. So plug flow reactor and mixed flow reactor almost similar values you are getting for CS max. 7.16. Here T is desired product and Ca0 is given as 5. T is desired product, so numerator will be your last equation, that is Ca square. Denominator remains same. So Ca square by 1 plus Ca whole square. At low value tending to 0, this is 0. At high value tending to infinity, this becomes 1. So your yield varies from 0 to 1. Plug flow reactor CT max, same equation, same method, only here numerator changes. So this thing will change. So for this integral, x square dx by 1 a plus bx whole square, same. So solution is 1 by b cube. This is a plus bx minus 2a ln of a plus bx minus a square by a plus bx. Okay. With this, you can solve this, and outside we don't have anything, so I have just written 1. For you should remember, whatever is constant is there, it will come outside, so it is 1. And 1 by b cube, b is also 1, so it will remain as 1. A plus bx, 1 plus ca, and all this, a is equal to 1, b is equal to 1, you substitute, and from 0 to 5, if you solve this, substitute all the values and just solve it, upper limit minus lower limit, you get CT max value as 2.25. Okay. So if T is desired product and Ca0 is equal to 5, this value comes out to be 2.25. In mixed flow reactor, again exactly same method, only this numerator is changing and Ca0 value is changing. So maxima this equal to 0. So I have not written all those, again quotient rule, all those terms. So here you can solve this, and you get this equation, and this will give you Ca is equal to 2. CT max at Ca is equal to 2. So in mixed flow reactor it is 1.333. And you can make a plot for this function between 0 to 5. Up to 5 you can take the values. I have taken it up to 4 here because I am interested in this maxima. It is reached here, and this value is here. This is 1 and 1.5. So 1.33. For this problem, you try by numerical method as well as graphical method, and you should get this 2.25. So we'll stop here, and in our next lecture we'll try to complete all the remaining problems from chapter number 7. So we stop here today.